I am Attila, a PhD student with Claudio Castelnuovo at the University of Cambridge, and I'm going to talk about our work on neural network wave functions and the sign problem. To give an overview of the talk, neural network wave functions in principle are a very powerful approach to quantum many-body physics. However, many state-of-the-art approaches suffer from the sign problem. And our contribution to solving this problem is a neural network ansatz and an optimization protocol tailored for learning non-trivial sign structures accurately, which works excellently on conventional unfrustrated antiferromagnets. And when we apply our method to frustrated magnets, we found very low energy unfrustrated variational states that may be important for a wider range of numerical methods as well. The basic idea underlying our work is that neural networks can represent any function at all, including many-body wave functions without any limitations on entanglement or anything else. The other appealing feature of neural networks is that we can optimize them or converge them to ground states using highly efficient machine learning codes. And examples of neural network wave function, the most famous example of a neural network wave function is the restricted Boltzmann machine. But based on that, several deep neural network wave functions have been proposed in the literature as well. As for the other half of the title, the Monte Carlo sign problem is usually associated with path integral Monte Carlo, where quantum dynamics is simulated as a classical stochastic process, but this cannot be done if the Hamiltonian has positive off-diagonal matrix elements, as is the case for antiferromagnetic and fermionic systems. The way this connects to our approach where we want to learn a ground state wave function is that in these sign problematic Hamiltonians, the ground state wave function has both positive and negative amplitudes. And while this shouldn't be a problem for the neural networks, because in principle they should be able to represent the sign structure, in practice, learning them in a variational manner fails. So one needs some approach or workaround around this problem, and obviously the best we can do is curing the sign problem where it is possible, but short of that, what is usually done is taking a wave function with a physically relevant sign structure, such as a mean-field fermionic wave function, and using the neural network merely as a sort of just wave factor to correct for the amplitudes. To demonstrate the sign problem a bit more concretely and show the system on which we benchmarked our approach, we consider the J1, J2 Heisenberg model on the square lattice. That is to say, we have a spin 1/2 on each vertex of a square lattice, where nearest neighbors and next nearest neighbors interact with each other antiferromagnetically. And because we have these antiferromagnetic triangles, this model is frustrated. But there are two unfrustrated limits. One is where there is no second neighbor interaction, only nearest neighbor interactions. And here there is a well-defined Nail order, which allows us to cure the sign problem with the so-called Marshall sign rule, which as well has this distinct checkerboard pattern, similar to the Nail order itself. And the other unfrustrated limit is where we only have a second neighbor interaction. Here the ground state order is stripy, and likewise, we can again cure the sign problem using a Marshall sign rule, which itself will have a stripy pattern rather than a checkerboard one. But in general, if we have both a J1 and a J2 interaction, the model is frustrated, and there is no simple sign structure that we could impose to get rid of the sign problem. And in this frustrated regime, between the Nail and the stripy order, there is also a valence bond solid and a spin liquid phase, which is a hallmark of strong frustration. And in this work, we studied 2 points on this phase diagram. One was the nearest neighbor only model, which is unfrustrated, and we also studied this point well within the spin liquid phase of the phase diagram. Going back to neural networks, the sign problem can be stated as the fact that learning the amplitudes and the phases of the wave function simultaneously tends to be unstable unless one supplies a good initial guess on the sign structure. And in order to improve on this, we start by separating the amplitudes and the phases of the wave function into two separate neural networks. But even so, typical neural networks would fail as an ansatz for the phase. So what we do instead is that we define a single convolutional layer. So it's a very simple neural network. And then every output of these convolution layers, which are just linear combinations of the spins themselves, are a guess of the phase. And the way we combine these many guesses into a single estimate of the phase, we treat them as unit complex numbers, and we add them up like this, so that the overall phase is a sort of average between the several individual phases. So now we have a parameterization of our wave function, and now, in order to converge it to the ground state, we attempt to minimize its variation energy, which is just the expectation value of the Hamiltonian. The problem we have here is that the natural initialization of our neural network will mean that all the phis, or the phases, come out close to zero, and that is essentially a ferromagnetic sign rule, because all the wave function entries would be positive. And if we start from here and attempt to learn an antiferromagnetic sign rule, that tends to be unstable. So in order to fix this problem, we perform the two-stage optimization. So we start by forcing all the amplitudes to be constant and optimize the phases only, so that we can achieve a broadly antiferromagnetic sign structure without introducing any instabilities. Afterwards, from this starting point, now we can optimize both the amplitudes and the phases without incurring any instability. And now we can see on this plot of the variational energy evolving across the optimization protocol, our approach, which is shown by this blue curve, achieves a very good variation energy, very, very close to the exact ground state, both in the unfrustrated nearest neighbor model as well as the fully frustrated spin liquid case. So again, we achieve a very good variation energy, which is on par with the state-of-the-art variational approaches. And what is also shown in this graph by the red and green curves is that if we use other neural networks to parameterize our phases, that tends to fail. We get an energy very far from the true ground state, and the wave function itself is clearly very develops all sorts of instabilities, as we can see it from this plot. And finally, to say something about the actual sign structures, we can compare a sampling of the neural network, the phi, to the physically expected sign structure of the true ground state wave function. But also, because the ansatz that goes into this capital phi is so simple, we can go back and directly interrogate the kernels that appear in the convolutional ansatz. So in the unfrustrated case, we expect a Marshall sign rule, and indeed the phase neural network reproduces the Marshall sign rule perfectly. And if we take an example kernel, we can see this distinct checkerboard kernel, which is again consistent with the Nail order and the Marshall sign rule. If we now go to the frustrated case, we can see that the kernel develops some stripy features in addition to the checkerboard features, which we can interpret as a sign of the competition between the Nail order and the stripy order. But if we then go back and check the distribution of the phases, we still see a precise Marshall sign rule, which we know is incorrect for this particular problem. And it is possible that our ansatz has a bias for Marshall type sign rules, so it fails to learn the minor deviations of the true ground state from the Marshall sign rule. But at any rate, the existence of such a state is an interesting physical insight definitely into this system, but possibly into spin liquids more generally. And this brings me to my conclusions. So we developed a neural network ansatz and an optimization protocol to capture and learn antiferromagnetic sign structures, and we verified it on the frustrated Heisenberg model on the square lattice. And we found that it works excellently in the unfrustrated case, but still has some issues and points to improve in the frustrated case. And I would like to draw your attention to our paper on the archive, and thank you very much for your attention.